iLearna. Learn today, lead tomorrow.
Welcome to iLearna listeners, and welcome back to the deep dive.
Great to be here.
Today, we're tackling some really technical stuff, but it's absolutely core to safety in the oil and gas world.
That's right. We're looking at a specific report from the International Association of Oil and Gas Producers, or OGP. It's report number 434-07.
Okay, 43407, and this is part of their risk assessment data directory.
Exactly. OGP's role really is to pool all that technical knowledge and, practical experience from companies worldwide.
Right, and turn it into guidelines, best practices, aiming for consistency.
Precisely. And this report zeroes in on consequence modeling.
Consequence modeling. So what's the official definition, according to the report?
Well, Section 1.0 puts it as calculating or estimating numerical values, basically describing the credible physical outcomes when you lose containment of flammable, explosive, or toxic stuff.
So figuring out the impact on people, equipment, safety systems.
Yes, predicting what actually happens physically.
Okay, so it's the science behind answering. If things go wrong, what happens? How bad could it be? Where does the danger go?
That's a good way to put it. Moving from the what if to the what then in numbers.
Our mission today, then, is to unpack this guideline. It's dense, no doubt, but we want to pull out the key ideas, the different approaches they use, maybe some surprising bits, too.
Sounds good. Paints a picture of how the industry tries to get ahead of potential disasters.
Let's start with the scope. What kind of consequences are we actually talking about modeling here?
The report lays out 6 main phenomena. And it's important to note, this specific report is about safety impacts people, assets. It explicitly excludes environmental impact modeling.
Okay, safety focus. What are the 6?
It starts, logically, with the release itself, the initial discharge.
Step 1, it's out.
Step 2, where does it go? That's dispersion in air or maybe water.
And once it's spread out, if there's a spark?
Then you could get fire and the resulting thermal radiation. Or, if conditions are right, particularly with confinement or congestion. Right. Fire and explosion are the big immediate hazards.
But there's more to it.
Yeah. Even without ignition, the cloud itself can be dangerous. So number 5 is smoke and gas ingress. Think getting into buildings, safe havens.
Like temporary refuges offshore.
Exactly. And finally, number 6 is toxicity. The direct harm from breathing the substance in.
Release, dispersion, fire, explosion, smoke, gas ingress, toxicity. It flows logically. I think figure 2.1 in the report shows how they connect, right? Dispersion leads to many of the others.
It does. They're highly interrelated. And understanding that sequence is key because for each of these phenomena, the report discusses different ways to model them.
Different levels of complexity, I imagine.
That's right. Generally 3 types of approaches. First, you've got simple correlations or formulae, quick calculations, often based on past experiments or basic physics.
Like Bernoulli's equation for flow out of a simple hole?
That kind of thing, yeah.
Yep.
Then there are general-purpose consequence modeling software packages. More integrated, handles more complexity.
Okay. And the third?
The most detailed. Computational fluid dynamics, or CFD.
Ah, the supercomputer simulation.
Pretty much. Simulating fluid flow, heat, reactions in 3D, really powerful for complex shapes like inside a packed process module offshore.
So simple gives a rough idea, software gives a standard picture, CFD gives the high-def simulation?
Roughly, yes. But here's a critical point the report hammers home. Whatever method you use, simple, software, CFDD, you have to understand its limits.
Know your tool.
Exactly. Is it valid for your scenario? What data does it need? How sensitive are the results? Can you check if the answer even makes sense? You can't just blindly trust the output.
That's crucial. Okay, let's walk through the sequence then, starting with the release itself, section 2.1.
Right. Release modeling. It's all about defining the source term. What's coming out, how fast, what state is it in, temperature, pressure, liquid, gas.
And is the release rate constant?
Good question. Sometimes simple models assume it is, based on initial conditions. That might be okay for, say, far-field effects onshore.
But not always.
Not for things like offshore platform incidents or pipeline breaks. There, the initial high rate matters hugely for how quickly things might escalate or how long a refuge needs to last.
Right.
And for pipelines, the pressure drops as it empties. So time-dependent modeling, which captures this changing rate, is often preferred. Using a constant initial rate can massively overestimate the total hazard downwind or over time.
Makes sense. Time matters. What else does the release model tell us?
It needs to predict the physical state, vapor, liquid, or often a two-phase mix. And if it's two-phase, a key output is the liquid droplet size.
Why droplet size?
Because that determines how much liquid might just fall out near the source rainout versus staying airborne as an aerosol, which can travel further and contribute to a flammable or toxic cloud.
Ah, so it directly feeds into the next step, dispersion.
Exactly. And the report gives some great visual examples here. Figures 2.2, 2.3, 2.4. They show actual release rate calculations.
Let's see. Figure 2.2, natural gas. Wow. A 50-millimeter hole at 100 bar is over 350 kilograms per second.
Huge flows. Figure 2.3 for propane shows similar scales and how pressure affects whether it's vapor or two-phase. Figure 2.4, kerosene, lower mass flow, but still a significant liquid spill potential.
Seeing those numbers really brings home the energy involved.
It does. And modern software can handle all this complexity, changing flow rates, flashing liquids, complex vessel shapes, long pipelines.
What about buried pipelines? That sounds extra tricky.
It is. You've got flow from both ends, plus the soil interaction. For a full rupture, they often model an initial blast phase, maybe a fireball if ignited immediately, then a longer lower flow phase for dispersion modeling.
And for smaller leaks?
For leaks big enough to blast through the soil, they suggest a simplified quadrant model, sort of modeling jets going up, sideways, and down, but accounting for ground effects.
Okay.
For really small leaks that just seep through the soil, it's more like diffusion modeling. It shows how they adapt the model based on the physics of the situation.
Fascinating practical detail. Okay, material is out. Now where does it go? Section 2.2, dispersion and ventilation.
Right. Goal here is predicting how it spreads and mixes, what concentrations you get where.
And the environment matters hugely, right? Open air, onshore versus inside an offshore module.
Absolutely. Onshore, it's wind, atmospheric turbulence. Offshore, often it's about ventilation inside structures. Figure 2.5 shows the main types of atmospheric dispersion. Jet dispersion right at the source if it's high pressure.
Momentum driven.
Then, if it's denser than air, heavy gas dispersion where it slumps and spreads.
Hugs the ground.
Until it dilutes enough to behave passively, like smoke from a chimney that's passive, or Gaussian dispersion. A release might go through all three phases.
Are there simple models for dispersion?
There are, but they're quite limited. Basic Gaussian equations work for passive dispersion over flat open ground. For inside spaces, the simplest is the CSTR model, continuous stirred tank reactor.
CSTR sounds like you assume everything mixes instantly and evenly in the whole room.
You got it, like dropping dye in a perfectly stirred bucket. Very simple, often too simple for real situations. There are also simplified workbooks for gas buildup offshore.
And for spills or underwater releases.
Simple models for oil pool spreading exist. For subsea gas, a common rule of thumb is assuming the plume hits the surface with a diameter about 20% of the water depth. That then becomes the source for an atmospheric dispersion model.
The report has examples here too, figures 2.7 and 2.8. They really show the impact of weather, don't they?
They really do. Look at figure 2.7, flammable distance for a vapor release. Compare stable low wind conditions, that's F1.5, versus neutral windier conditions, D5.
Wow, the flammable cloud is way bigger under stable conditions.
Much bigger. More wind mixes and dilutes it faster. That difference isn't trivial. It changes the whole hazard zone.
And figure 2.8, two-phase releases, the distances look shorter sometimes.
Yes, potentially. If a lot of liquid rains out, it's not contributing to the airborne flammable vapor cloud immediately. Again, it shows why getting that source term right, including rainout, is so important.
Simple models clearly have their place, but limitations too. What about software and CFD?
General software often uses box or bloom puff models, better for open areas, further downwind. CFD really comes into its own for complex geometry congested areas, buildings, offshore modules.
And CFD is pretty standard offshore now.
Oh yes, standards like NORSOC ZDAIR 3 basically mandate it for understanding ventilation and how gas clouds would behave inside modules. You use it to find the credible worst-case cloud size, location, concentration under various conditions.
And that worst-case cloud then feeds into explosion modeling.
Exactly. It's a crucial input.
Setting up those CFD runs sounds like it involves a lot of choices.
It does. Wind direction, leak location, rate. You can't simulate everything. So engineering judgment is key. They use techniques like symmetry or sometimes a frozen cloud concept to get representative worst cases without endless simulations. It's also used to optimize detector layouts and ventilation design.
Okay, released, dispersed, now ignition. Section 2.3, fire and thermal radiation, and 2.4, explosion. Let's take fire first.
Fire modeling aims to predict flame size and shape, and importantly, the heat radiation reaching surrounding areas or people.
different kinds of fires.
Several. Flash fires, quick burn of a cloud, no big pressure wave. Jet fires from pressurized releases. Pool fires from burning liquid spills. Boilover in storage tanks. Fireballs, or BLEZs, it's boiling liquid expanding vapor explosion, think LPG tanks. And even crater fires from ignited buried pipeline leaks.
Are there simple ways to estimate these?
Yes, simple correlations exist for, say, jet fire length. The report gives approximate radiation distances using the Chamberlain model. Table 2.1 provides burning rates for different liquids to help calculate pool fire size.
Let's look at the examples. Figures 2.9 and 2.9 for jet fires.
Figure 2.9 shows how radiation distance changes with propane release rate. Figure 2.2 shows the effect of releasing higher up the ground level radiation footprint changes.
And figures 2.1 and 2.12 for pool fires? Figure 2.12 looks odd. The distance to 12.5 kilowatt-hour or not goes down for really large pools.
It does, and that's a brilliant example of needing to understand the model you're using.
Shouldn't bigger fires always mean more heat further away?
Logically, yes. But the report explains this specific simple model predicts that for very large pools, the average heat radiated per unit area actually decreases, maybe due to soot-blocking radiation from the center. It's a model artifact, essentially.
A real buyer beware for relying on simple models blindly.
Absolutely. Critical review is essential. For things like boilovers or BLEVs, there are also simple models, like Prue's model for fireball size and duration based on the mass involved. Interestingly, the boilover height estimate mentioned is based on watching videos of a real tank fire.
Practical observation feeding back into the models. Software handles most fire types.
Yes. General consequence software models, jet fires, pool fires, fireballs. CFD is used for detailed heat load analysis on structures, especially complex ones. There's guidance from Oil and Gas UK on this.
And CFD ties into defining design loads.
Right. Figure 2.14 shows a probabilistic approach using CFD. You simulate many fire scenarios, combine with frequencies, and determine a dimensioning accidental load, or DAL. It's about designing for a credible fire, not necessarily the absolute worst imaginable one, optimizing safety.
Okay, let's switch to the other ignition outcome, explosion. Section 2.4, often the big one for structural damage.
Primarily, we're talking vapor cloud explosions, VCEs. Huge progress here, especially after large-scale tests like at Spadenham.
And the report says the old confined and unconfined labels aren't quite enough.
Not really. It's better to think about degrees of confinement, solid walls, and crucially, congestion. Pipes, vessels, structures.
Yeah.
They create turbulence as the flame rushes past.
And turbulence speeds up the flame.
Dramatically. Faster flame means higher pressures, bigger bang. Congestion is key.
What about simple explosion models?
Historically, things like TNT equivalents were used, based just on the flammable mass, but they don't capture the critical effects of geometry and congestion well.
So what's used now in software?
Onshore, models like TNO multi-energy or Baker-Strelo tang are common in general packages. Multi-energy divides the cloud and assigns a strength based on congestion level. Baker-Strelo tang uses parameters like reactivity and obstacle density. Getting the inputs right, especially for congested areas, takes real expertise.
And offshore?
Offshore, CFD is routine now for probabilistic assessment, driven by standards like NORSOC Z013. The probabilistic approach combines lots of CFD explosion simulations for different clouds and ignition points with frequencies to get exceedance curves, the likelihood of exceeding a certain pressure.
Sounds computationally intensive.
It is, but it gives a much more realistic picture of the risk, allowing for optimized design rather than potentially huge overdesign based on crude, worst-case assumptions.
How does the CFD for explosions work?
You take representative gas clouds from your dispersion modeling. One challenge is simulating ignition in a turbulent cloud. Often an equivalent quiescent cloud is used, like the FLACS-Q5 approach. You then simulate ignition at various points, especially near congestion, because ignition location matters a lot.
And the output is?
Overpressures at different locations, and the drag forces those pressure waves exert on structures. That's what engineers need for design checks.
Okay, fire and explosion covered. But even without ignition, the cloud is still a problem. Section 2.5, smoke and gas ingress, and 2.6, toxicity.
Right. Smoke and gas ingress is vital for assessing temporary refuges, living quarters, escape routes. You model the source, the dispersion, how it gets in, and the effects inside.
Source could be smoke from a fire or a toxic gas release itself.
Exactly. For smoke, Table 2.2 in the report is useful, giving typical smoke compositions, KEO, CO2, particulates depending on the fuel and fire type.
Dispersion of smoke seems tricky. Hot gas rises, right?
Usually, yes. And simple models often predict that. But the report points to the Piper Alpha disaster, where smoke traveled horizontally along decks. It suggests simple, hot, buoyant plume models might not always capture reality, maybe due to sit density. Sometimes experience-based rules for horizontal travel are used instead.
Wow, a direct lesson from a tragedy feeding into the models. How about ingress into a building, or TR?
This simple CSTR model pops up again, assuming perfect mixing inside. More advanced are multi-zone models, dividing the space up, and CFD can model it too.
How is CFD used for ingress?
It can predict how external airflow carries smoke or gas towards ventilation intakes. Very useful during design to place intakes optimally to avoid sucking in hazards.
And finally, toxicity, section 2.6.
Focused on acute effects from accidental exposure. Think H2S and sour gas, chlorine, ammonia, and of course smoke components like carbon monoxide.
How do you model the harm?
It's all about dose response. The dose depends on concentration, C, and exposure time, T. Often it's expressed as C raised to the power n multiplied by T, so CNT.
C to the power n, that n value matters.
Hugely. Look at table 2.3. For carbon monoxide, n is 1. Dosage is C times T. Simple. But for hydrogen sulfide, H2S, n is 4.
N equals 4? What does that mean practically?
It means concentration is far more dominant than time for H2S toxicity. Double the concentration for half the time.
Yeah.
For CO, the dose C2 is the same. For H2S, the dose C4T becomes 8 times higher. So for high-end substances, short whiffs of high concentration can be much deadlier than longer exposures to lower levels, even if the simple C times T is similar. It fundamentally changes the risk profile.
That's a really critical insight.
It is. The report mentions the UK HSE approach, using specific dose levels like SLT and SLOD, defined by C and T values. The most complex method is using probit equations to get a probability of fatality.
And software can calculate these lethality levels.
Yes, general packages often calculate probits and map out lethality contours. CFD gives you the concentration field, which you then feed into the dose calculations using SLOD or probit equations.
We've covered a huge amount of ground there following the consequence chain. Section 3.0 gives guidance on actually using these models.
And the headline message is crucial. Models are imperfect. They simplify reality. You always need reality checks, expert judgment.
What sort of uncertainties does it highlight?
Things like QRA often uses simplified scenarios, not full chaos. Weather is assumed constant. Simple models ignore barriers. CFD has its own issues with turbulence modeling, boundary conditions.
So choosing the right tool is key.
Absolutely. Depends on the study scope, the depth needed, the scenarios, who's doing it, the data available. Integrated software is common for full QRA, but you need to understand it. Simple might do for screening. CFD is standard for offshore explosions, increasingly used onshore for critical stuff, but it needs real expertise.
Yeah, I mentioned CFD geometry and something called PDR.
Yeah, porosity distributed resistance. For explosion CFD, you can't model every single pipe and cable tray in detail, but they all contribute to congestion and turbulence. PDR is a way to represent the effect of that dense clutter without modeling every item. Getting that density right is vital for pressure predictions.
Like modeling wind through a forest without modeling each leaf.
Good analogy. And if you're early in design without full details, you might apply growth factor or add representative congestion based on similar plants.
The report also points to data sources and validation studies, right? Sections 4, 5, 6.
Yes, key references like the CMPT guide, Lee's loss prevention, mentions validation work like SMATIS for dispersion, SPEDETM GIPs for explosions. It's interesting how some methods have practical roots buried pipeline modeling based on confidential data, the boilover height estimate from that video. Essential reading if you need the deeper detail.
Okay, what a journey. We've really gone deep into this OGP report's systematic world of consequence modeling, release, dispersion, fire, explosion, smoke, toxicity, using everything from basic formulas to complex CFD.
And understanding these approaches, even conceptually, gives you a real appreciation for the technical work behind safety assessments. It's not just guesswork. It's a structured attempt to quantify potential hazards.
So this deep dive was based on our reading of IOGP Report number 43407. And remember, our conversation is our interpretation of its contents.
Definitely. For the full picture, the specific equations, all the figures, the detailed context, you really need to go to the original report.
We strongly encourage that. And if you have read it or have questions based on our discussion, please share them.
We'd love to hear your thoughts.
Leave your comments and questions below the video on our YouTube channel. We always enjoy continuing the conversation there.
Now, for a final thought to leave you with, something the report itself touches on. Despite all this sophisticated modeling, these detailed guidelines, the sheer computing power involved. The report acknowledges that models are imperfect. reality can always throw a curveball.
So what does that tell us about the role of people? The experience, the judgment, the constant learning, the operational discipline. How essential is that human element alongside these powerful predictive tools in truly managing risk and ensuring safety?
Something to ponder. Thanks for joining us for this deep dive.